God willing, we will finish today in the city. We talked last time about transportation. We discussed a bit about it last time, and we walked around the city a bit. We can talk a little today about, and we will talk about After discussing the detector and the types of detectors available in computed tomography, CT, we will talk about the concepts of slice thickness and interval and their effect on image quality. After discussing the types of detectors and the types of detectors related to slice thickness, we will address image quality, noise, contrast, and resolution in CT. We will talk after we discuss the types of detectors, and we will talk a bit about slide thickness. We will also discuss the noise and the artifacts present in the CT. We have discussed X-ray imaging in these sections, which share the same concept and principle, but some things will be different or additional. After that, we will talk about CT image reconstruction. We will discuss how the image is produced and formed, and you often hear someone say, I use filter back projection, or I use iterative reconstruction algorithm. We will understand exactly what filter back projection means and what iterative reconstruction algorithm means, without delving into some of the mathematics involved, but hopefully everything will be clear for you. After discussing image quality, we will talk about the artifacts in the physics of CT artifacts, including ring artifacts, partial volume, cone beam artifacts, metal artifacts, and photon starvation. We will discuss CT dosimetry and dose calculation. What will we discuss next? How do we calculate the dose in relation to it? What are the topics available on the summary page that you can use, or how to improve the calculation of the dose that you can rely on, or how to calculate the dose for me, we will quickly go through the slides that are available. Of course, we know the main shape of the CT system. I have a gantry like this, and I have a table or couch, and I have the bore where the patient enters. The gantry, of course, contains the X-ray imaging tube, and on the opposite side, I have the detector. The shape you see here is the laser that I use for alignment. I have a laser that is positioned in front of the patient, and there is one lateral laser. The lateral laser is used to determine the height of my couch. The patient must be aligned so that the lateral laser is centered on the patient's body, ensuring that the patient is centered in my field of view, neither too high nor too low. The front logic must be present in the middle or in the front logic so that the front logic is not present in the more front logic so that the front logic is not present in the front logic so that the front logic is not present in the more front logic so that the front logic is not present in the front logic. The components of the gantry comprise of components such as include the X-ray tube, which is positioned in front of the detector. There is a tube controller that regulates and controls precisely, manages and operates efficiently the tube, and a high-frequency generator that provides supplies, delivers effectively the voltage, or generates, produces a potential difference we discussed earlier on previously mentioned before, which can be either triple phase or high-frequency voltage. Additionally, moreover, there exists an onboard computer system that controls every single one of these various components inside, contained and housed in the gantry setup, and transmits, sends, relays information, data details to another stationary, fixed, immobile computer system which connects, links, joins, ties together all these different gantry components to yet another separate, distinct, different computer located, situated, placed, date in the console control room area. This entire setup, arrangement, configuration is clearer, more understandable, easier to comprehend when considering looking at focusing on the X-ray tube system, collimator device, high voltage generator setup and detector system. The procedure operation consists of both the X-ray tube device and simultaneously working alongside the patient subject individual person being examined, tested, checked out while simultaneously at the same time the detector device captures, records, takes note of the detected, transmitted, sent outgoing X-ray beam signal as both simultaneously, concurrently, at the same time. The X-ray tube device rotates, spins, turns around together alongside the patient subject individual being examined, tested, checked out by it. The detector then translates the need, converts, changes this detected, captured, recorded, transmitted signal into our final resulting image. This is the X-ray source, and this is the beam, and this is the detector. We talked about the types of generations between single, first generation, second, third, fourth, and fifth generation that exist. We discussed what it means when I say I have a single row of detectors or multiple rows of detectors and their number. This makes a difference in the machine, the coverage area, the scan time, and the dose. This is, of course, the shape of the machine and its components which undergo rotation, and today this rotation takes 0.3 seconds. Some machines can reach a rotation time of less than 0.2 seconds, allowing for about 5 rotations per second, which is quite impressive in terms of speed and efficiency. We have talked about the collimator and the bow tie filter, and we discussed the collimator in relation to filtration, as we have previously mentioned in our discussions. Now, when we talk about the detector, I want you to imagine that I am looking for a detector to perform detection of the transmitted beam from the patient. I have an X-ray tube and a patient. The detector must have high efficiency to achieve effective detection, meaning it should have high detection efficiency to detect the transmitted beam to ensure optimal performance and accuracy in the detection process. Additionally, the detector should be sensitive enough to detect a wide range of radiation intensity or energies, not just operating within a specific range, to cover a broad spectrum of radiation and energy levels, which is crucial for comprehensive analysis and diagnosis in medical imaging and other applications where precision is key and reliability is paramount. I want it to have a wide detection range. All right, the second point is if I have here is the patient, and here is the X-ray tube, and here is my detection device, or the detection device element. As you can see, the detection device element should be smaller. The smaller the detection device element, or my detection device width, the more this increases. What I mean is that what comes out, I want to say that the detection from the patients has undergone investigations regarding how much the more the patients are able to achieve it. What percentage of detection did the patient achieve? What percentage of detection did the patient achieve? How capable is the detector in being able to perform detection? A high fraction or percentage of the transmitted X-ray beam that comes back from the patient is significantly important at this time, as it relates to geometric efficiency. This geometric efficiency is very crucial and can be significantly affected by the dimensions of the detector, the position of the detector, and the gaps present. For example, if I have the patient here and the detector here, and I divide the detector into elements, if there is a gap between this detector element and the adjacent one, then there is a part here that significantly reduces the geometric efficiency, which in turn significantly decreases the percentage. The mission must be assigned. It should be sent at night. I need the size to be assigned to me first so that I can get more resolution, so I need more resolution. As I mentioned, I divide the topic into rows or day sections, with each page containing about 200 or 2,000 detectors, of course, depending on the manufacturers and the effects of the machine. In the past, a certain type of detector was used. The text discusses the use of xenon or krypton gas, where the idea is that the transmitted X-ray photons interact with the gas to create ionization, resulting in negative and positive charges. The chamber containing the xenon gas is connected to electrodes which create negative and positive electrodes. The positive electrode collects the negative charge, while the negative electrode collects the positive charge, generating a current. This current represents a signal which indicates the incident intensity of X-ray photons that have already been transmitted from the patient. There were issues with xenon gas as its detection efficiency is around 50%, which is low. I need something that provides a detection efficiency higher than that of xenon gas, even though it was not expensive. The low efficiency means that I would need to increase the dose to compensate, which is a problem. So I need to address this issue. They made a change to the story with sodium iodide, or the solid state detector, completely eliminating the use of gas detectors because they had problems, especially since I couldn't use them with the fourth generator due to its specific geometry and shape. In fact, we thought that the fourth generator was like this, where the detectors were fixed and the X-ray tube was the one that moved. It tells you that, for example, the X-ray tube is moving around in the fourth generator, and the specific orientation of the gas detector is a tube that has a certain length. It mentions that at that time you couldn't capture the transmitted photons coming to you at certain angles. What could happen is that if they come at different angles, you have a problem because the detectors are fixed in a ring shape in the force, for instance. Is everything okay? So consider that not all tubes will be vertical to the X-ray beam. The transmitted X-ray beam might come at a certain angle, while the detector itself, whether it's a gas-filled detector or a xenon detector, won't align with the direction of the X-ray beam. In this case, it reduces the geometric efficiency of the gas-filled detector, which had issues like this. So they decided to replace this with solid state detectors. The solid state detectors allow for a smaller size and are based on the presence of scintillator material. The scintillator material receives the X-ray photons transmitted from the patient, causing scintillation. As we discussed, regarding scintillation, it excites an electron, which is ejected from its orbit, leading to excitation that produces visible light. This visible light is detected by a photodiode, which converts the incoming photon into an electrical signal. We know that the quantity and intensity of the signal correspond to the X-ray transmitted from the patient and hitting your detector element, which can reach up to 80%. The solid state detector has a small physical size and is commonly used now in all the CTs or computed tomography machines available. The idea is that these detectors are designed similarly to what we discussed in digital radiography, where we talked about TFT or detector size. If you remember, the pixels had a certain dimension. For example, in digital radiography, it ranged from 0.1 to 0.2 microns, which is small. In CT or computed tomography, the situation is a bit larger. How is it larger? If we talk about the width of the detector itself for a single row of detectors for a machine that takes axial scans, you might find the detector width itself is 15 meters. If you are talking about a multi-slice or multi-detector machine, the detector width can reach up to 0.5 meter. Why is it said to be so large, and what is its relation to image quality? Let me explain. Why and what? What is its relationship with determining the slides, the clarity of the image originally? I have here a single detector and here a multiple detector. This is the X-ray beam with the detector. And this is the X-ray beam coming from the X-ray tube. This is the collimator. When we talk about a single detector, what are we talking about? Do you remember the topic of penumbra? The penumbra is, of course, the region on the periphery where there is blurring or high unsharpness and less resolution. So, Someone asked me last time if there is something called beam width and something called nominal width. The width of the slice thickness is determined by the collimators present. The X-ray beam that is coming down, I adjust the collimator to reduce or narrow it, which determines my beam width. The beam is like this for me. This defines my beam, how the beam looks, and what its weights are like. In the past, when they used the single detector or single row of detectors, the idea was that it would determine itself whether to reduce or shrink the beam size. If I want an image of 5 millimeters, I would shrink the beam to 5 millimeters, making it 5 millimeters for me. If I want to enlarge it, I would make it larger. That's why it was also possible to use just one large detector weight, and it would reduce and enlarge using the data it received, which is what it uses for its signal. In the multi-detector, the situation is different. Why is it different? Because you have the rod of the detector itself, which contains detector elements, and each detector element has a specific size. For example, let's say I have a detector element that is 0.5 meter or 0.5 millimeters. If you want to take slices or images, each image or slice is taken at 1 millimeter. So what does it do? It says, well, I will take this region or this area. Okay, every two detectors together form 1 millimeter. So I will do a binning or a combination and take them together. Therefore, the first slice for me will be from these two detectors, which is 1 millimeter for me. After that, the next slice and the next two, and then the slice after that, each one of them will be 1 millimeter. So here, the thickness depends on the detector. The detector itself is in the multi-detector, in the multi-slice, but in the single slice or in the single row of detectors, the matter depends on the beam weights for me. If you come here, and notice, for example, you will find something. You will find the penumbra area here. You are taking 4 outside. Why? Because you want to eliminate the effect of the penumbra area. So how will you eliminate it? It is easy to eliminate it by making sure that your beam is now larger than the weights of the detector you want. Meaning, for example, you will take 4 or 5 slices, so you adjust your geometry. Sometimes they use what is called a pre-collimator and post-collimator, meaning there will be a collimator after the patient. This collimator opens and closes 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 and closes. I will work, for example, on the detectors in this area, this area, this area, this area, and this area that I have shaded. This area from here to here is the area I am working on. I will make my beam a bit larger because I want to avoid the penumbra area and I don't want to include it. So the area after the penumbra, or the area where my detectors are, where my slices are, should be far from the penumbra area. This way I can get a good image. I'm sorry, I just need to let one of the doctors in. Beautiful. This was the shape here. And when we use this shape, that's it. And here, of course, this is at a level, right? I mean, this is mine. Here is the multi-row of detector, repeated several times to emphasize its importance. This is the patient, and the patient name is structured this way so you can visualize it with me. This is the z-axis that works with the patient. For me, well, here we have the detector. As you know, I have 2 types of gas, which are xenon or krypton. And of course, there were issues with geometric efficiency. It also has a specific night with the topic we replaced with the solid state detector that uses scintillator material. When X-rays fall, light photons are emitted, which are received by a photodiode and converted into an electrical signal. The solid state detector has the advantage of high detection efficiency reaching 90%, and high geometric efficiency reaching 80%. You can achieve this in a small size, reaching 90% or 80%, and you can make it possibly down to 0.5 millimeters, allowing you to create slice thicknesses for images with a small footprint. Of course, this varies from manufacturer to manufacturer. Some companies may tell you they can provide a slice thickness of 0.5 millimeter, while others may say no, it's 1.25 millimeters. Depending on the machines and their versions, the detector specifications, rows of detectors, and detector width of the detector can vary significantly. Even if you are going to buy a machine, sometimes they will tell you they are selling a machine with 32 detectors or 16 detectors, but they might say that this device only has 8 rows of detectors. However, they claim to perform reconstruction with 32 detectors. So there are some aspects they play around with. It is very important for me to know this because it affects your control over the imaging process. It controls the efficiency set, it controls the overload set or the tube load set that will operate on the X-ray tube for you. It controls the scan time set. All of this is important. You need to pay attention to how many sets I have and how much beam collimation is available to me. When we talked last time, I mentioned, if you remember, the topic of beam collimation with types of detectors means that in multi-slice detectors, I have types such as linear detector, adaptive, and hybrid array. These 3 types, what is linear, what is adaptive, and what is hybrid array, let's take it step by step. The linear detector is the shape of the rows of detectors, and this is row 2 and 3 and so on. You talk about the Z direction concerning the patient lying down. Do you want to visualize the position of the detector relative to the patient to make the image clear? The same idea applies here. The same idea, or row position in a crowd, the same idea, the same idea, the same idea. The matrix array or linear detector means that I have all these rows or all the detector widths available. I have 16 rows of detectors and all the detectors in each row are equal in width. For example, I have 16 detectors, each with a size of 1.25 millimeters. What does it mean? It means that it can detect data or transmitted photons at a certain thickness of 1.25 millimeters, right? So if I use the 16 rows of detectors, each one will give me a thickness of 1.25 millimeters. This means that the volume that will be captured in all images will have a minimum thickness of 1.25 millimeter. Can I take a thickness less than that? No, I can't, but you can perform reconstructed thickness between 1.25 and 1 millimeter. So you can produce images of 2.5 millimeter, 5 millimeter, or whatever thickness you want, because the minimum thickness you are working with is 1.25 millimeter. You need to know the type of detector you have and its specifications so that you understand that you won't be able to produce an image less than 1.25 millimeter. If you need an examination with a thickness of 0.5 mm or 0.6 medus, then you know that it won't happen. Now, if I have the option to use 0.6, then you will find that your detector width has a thickness of 0.6, which is the minimum. But if I say now, for example, that I will use, for example, if I want to obtain a 2.5 millimeter slice, I will use 2 detectors, each with a width of 1.25 millimeters. So these 2 will effectively act as 1 for the 2.5 millimeter slice, as if they are 1 in 2.5 millimeters, which are 2 rows of detectors. If I have 4 rows of detectors and I use 1.25 millimeters, then it will be 4 times 1.25 millimeters. In this case, you have used 4 detectors, So your coverage area, if you want to calculate it, will be 4 times 1, which is approximately 2.5 and 5 millimeters. Therefore, you are covering an area in the rotation of 5 millimeters. For 1 at 2.5, it will cover 2.5 millimeters, and 16 times 1.25 is approximately 20 millimeters. Approximately 20 millimeters. All right, so how many detectors do you have, or how many rows of detectors will you use? The old thickness gives you the coverage area. If you have a thickness of 4.2.5, then you can talk about 10 millimeters in rotation for one turn. This old coverage area is the space you will be able to cover, and this indicates the minimum thickness that will appear in the image. I can derive from this what I call beam collimation. Each one of these is referred to as beam collimation. You will find that each machine gives you an option. If you have a 64 machine, it tells you that you cannot operate at 6401 or 6414 repeated multiple times. For example, we say 1 in 2.5 or 4 in 1.4 or something like that. This option varies from one function to another, from one company to another, and from one model to another, right? Because it depends on the type of ray or the type of detectors you have. But you need to understand that these numbers mean something. For instance, 16 means 16 rows of detectors, okay? Yes. The number next to it represents the thickness of the section it uses, which is the product of the two standing together. This is related to the coverage area. What is this whole story called? It's called beam collimation. Beam collimation is the first type of detector, which is the linear detector, where all the elements present in it are equal in their weights. Then they mention the second type, which is